Hello, everyone. I'm your host, Ryan Murray, and I'm excited to welcome you back for another session of our Advanced Air Mobility Webinar Series. Today's presentation features FAA Wake Turbulence Research and Development Program, how it has evolved over the years, and how the wake assessments are accommodating advanced air mobility aircraft such as electric-powered lift. If you have any questions, please submit them using the YouTube live chat function, and we will have some time to answer questions towards the end of today's webinar. Jessica Sipnewski, Deputy Assistant Administrator for NextGen, will get us started. The Office of NextGen is the FAA's focal point on advanced air mobility issues and is coordinating key projects across many parts of the agency that will be required to integrate the new technology into our airspace system. Welcome, Jessica. Over to you.
Thanks, Ryan, and welcome everyone to our third installment of this AAM webinar series. Over the past few months, we've updated you on FAA's near-term activities for AAM, the proposed SFAR for powered lift aircraft, our research partnerships, and the development of vertiport standards. We welcome your suggestions for upcoming topics, as the aim of these webinars is to keep everyone up to speed on this fast-evolving new era in aviation. Additionally, you should know we're taking our discussions on the road, so to speak, by participating in the Transportation Research Board's annual meeting, the Volpe Thought Leadership Series, and coming soon at South by Southwest. And if you're going to be there, drop by and say hi to Sean Kazika. He'll be speaking on our behalf. I mentioned Volpe because our main presenter today, Jillian Chang, worked on her first wake project as an intern at Volpe while studying aeronautical engineering at Boston University. She's been with us here at the FAA since 2016 as our lead for wake turbulence research and development. The information we've been gathering on wake data has been a game changer, helping us to modernize the separation standards that controllers use across the country through the wake recategorization program. So let's take Memphis International Airport, for instance. I'm sure Jillian will cover some of this coming up, but a decade ago, as part of the early implementation of wake recat, the FAA safely reduced the separation from 4 nautical mile standard to 2.5 to 3.5 nautical miles, depending on the aircraft. With that reduction, controllers were able to clear 14 additional aircraft per hour, and we were also able to reduce time waiting on the ground by an average of 3 minutes, which reduced emissions. As a result, FedEx reported saving $1.8 million in fuel costs each month. In 2022, the FAA wrapped up the final site implementation for consolidated wake turbulence standards. As a result, we harmonized separation reductions across 93 TRACONs and 330 air traffic control towers, leading to improved efficiency at many constrained airports. So Jillian's team's research also contributes to our technical wake assessments ongoing in the operation every day. The FAA established a cross-agency wake turbulence team that collaboratively reviews reported wake events and leverages data from many sources to identify and mitigate systemic wake risk in the NAS. This important safety work has captured a lot of positive attention. Last month, Secretary of Transportation Pete Buttigieg presented the Transportation Safety Award to the FAA Wake Turbulence team, and Jillian was one of 10 individuals from various FAA offices who were acknowledged. Last summer, that same team was recognized by the FAA with our Data Excellence Award for creating, developing, or using data to drive insights to improve safety and as evidence to support policy development. I bring up those awards because I believe they highlight our team's credibility in the field of wake turbulence research and application. Our approach is rooted in science and driven by data, prioritizing safety above all. As new aircraft like eVTOL join the National Airspace System, they'll be assessed using this well-established process, contributing valuable insights back to our future applications with the data collected, and also making sure that we can integrate them for initial entry into service seamlessly. I hope that you find Jillian's presentation informative, and as Ryan said, if you have any questions for Jillian, just put them in the chat. So thank you again for joining us today, and Jillian, I'll toss it over to you.
Great, thank you, Jess. Good afternoon. I'll talk today about wake turbulence, about the kind of research we do here at the FAA and how it relates to advanced air mobility. So for wake turbulence, every aircraft in flight generates wake turbulence. These vortices are generated from the wing, and they're created from the air pressure differential over the surface of the wing. And that pressure differential causes the mass of displaced air to roll up and form counter-rotating vortices that we refer to as wake turbulence. The picture on the right on this slide shows a depiction of those two counter-rotating vortices coming off of the wing of the aircraft. These vortices descend and decay over time, and strong vortices can sometimes descend more than 1,000 feet. The picture on the left shows the descent of wake vortices. The strength and the wake age of a wake vortex depends on many factors that are specific to the type of aircraft that are generating the wake. So in this picture, you can see the larger aircrafts are outputting stronger wakes. The smaller ones are outputting wakes that are a little bit weaker. The factors that affect the wake strength can include wingspan, wing loading, the distribution of the weight over the wing, and very importantly, the aircraft's speed. Wing configurations such as the positions of the flaps and the air density, how the altitude also play a factor in the characteristics of a wake vortex, its strength and its decay time. So the FAA Wake Turbulence Research Program, we analyze proposed and current procedures for wake safety and efficiency improvements. For example, just mentioned our wake recap work. Aircraft have been historically classified by a single metric, which is mass gross takeoff weight. That metric classed the aircrafts into heavy, large, small, and then later super weight classes that have wake separations associated with them. We do know that there are more factors and parameters than just weight alone that affect wake behavior. With RECAT, we tried to separate those factors for our separation assessments. So our team sought to define separations using factors that more accurately affect the wake behavior and to reduce the inefficiencies in that 4 weight class system. We were able to increase efficiency by recategorizing aircraft while maintaining that same target level of safety. The Wake Turbulence Program at the FAA researches future automation updates to increase efficiency and safety in the NAS. Using that recap example, we are working on a dynamic pairwise wake separation solution that could take advantage of future automation systems and dynamically change wake separations based on current and forecasted winds from both ground sensors and aircraft-based observations. Wake separations can be safely reduced by taking advantage of stronger environmental winds, as wake decay is accelerated by ambient turbulence caused by winds. The Wake Turbulence Program at FAA also provides wake separation recommendations to the Air Traffic Organization for controller guidance. This is the current area in the body of my team's work that intersects with the work the FAA is doing for AAM integration. With a focus on AAM vehicles, we are assessing each vehicle as an aircraft that generates wake vortices and the behavior of those vortices based on wake-based factors. So that are factors beyond mass gross takeoff weight. We are developing an understanding of the wake encounter effect on loss link command and control that these powered lift vehicles have. The bread and butter of the FAA's Wake Turbulence Research Program is our data collection effort. We use this to capture and understand wake behavior using real data with sensors fielded. Our wake data collection is focused on gathering data in situ from real life situations from those wake generating aircraft. So our current wake data collection campaign uses established sensor locations at airports, currently San Francisco International Airport and JFK Airport in New York, that have a high number of significant wake generators, namely heavy and large aircraft, as larger airframes generally produce a stronger wake profile. Our database of wake behavior feeds into the development of our wake models. We use these models to analyze aircraft for procedure development and wake separation recommendations. This data informs our wake separation recommendations for smaller vehicles, such as AAM aircraft. The types of data that our data collection effort captures is wake vortex position and strength as a function of time, atmospheric conditions like the wind at the time the data was collected, and aircraft type. With this database, we can use that to apply into our models and calculate, assess all sorts of different procedures and separation standards. The FAA Wake Turbulence Program has existed since the late 90s, though research and data collection on wake vortices and wake behavior has been going on since 1970s, namely through NASA's research programs. The evolution of wake measurements and tools went from using aircraft smoke visualizations in the 1970s to using acoustic radars in the 1980s to the building of wind lines in the 1990s. Wind lines were a line of propeller anemometers along the end of the runways that would capture the strength and the transport of the wakes along the ground as the aircraft land. Our current measurement tool is a set of pulse lidars you can see there on the right-hand side that were required by our team in the early 2000s. The pulse lidar works by measuring the movement of particulate matter in the air and is distributed as it is disturbed by wake turbulence. Our sensors are placed to capture both wake in the region we call OGE, or out of ground effect, as well as NGE, or near ground effect. OGE is a region where you typically see vortex roll up with a nice circular vortices, and where you see a typical descent and decay. NGE describes a region approximately 1 wingspan above the ground, where the vortex interacts with the ground. They will move outward and they will decay faster. Wake turbulence separations are assessed using specifications and performance characteristics of the aircraft, both as an aircraft generating a wake and an aircraft encountering the wake. The wake turbulence separations are applicable when the air traffic organization is providing separation services. For example, in IFR or instrument flight rules. Aircraft with no published wake turbulence categorization and separation will receive by default 10 nautical miles in front and 10 nautical miles behind. It'll receive a no wake designation in the automation system. This is for aircraft that have not been assessed for wake turbulence that may have entered the system. And the 10 in front and 10 behind is used for conservative safety separations. So the FAA assesses and recommends separations smaller than that 10 nautical miles prior to aircraft entry into service. The goal of that is to reduce any constraints and capacity in that airspace. It is our goal to do that separation recommendation, separation assessment prior to entry into service so that those aircraft would receive something smaller than that 10 in front, 10 behind. The timeline on how quickly that happens is really dependent on an understanding on the aircraft's performance specifications and operating profiles. Additionally, rulemaking and procedure development for the integration of AAM vehicles may show that further analysis for wake on AAM operations may be required. All aircraft have type designators that's assigned from the International Civil Aviation Organization, or ICAO. We can see up to around 100 new ICAO type designators per year, and those we can be asked to provide wake separation recommendations for those up to 100 new designators. These aircraft can include traditional fixed wing aircraft, UAVs, and now powered lift advanced air mobility aircraft. All of the aircraft that we provide separation recommendations for follow this basic process outlined on this slide. The FAA receives notification of a new aircraft type, either from the manufacturer or an updated ICAO type designator list. And if the specification and performance data is not available publicly, the FAA connects with the manufacturer, or in some cases, an operator of that aircraft. The FAA uses proven methodology to develop a wake turbulence separation recommendation. The analysis required for developing a separation recommendation can be straightforward or it can be more complicated, depending on factors like aircraft complexity. For example, multi-rotor aircraft versus traditional fixed-wing aircraft, or aircraft that are close to the boundaries of existing aircraft categories. The timeline for developing recommendations can vary from a few days to over a year, depending on those factors. The development of the separation recommendation of the Boeing 777X took quite a bit of time due to parameters like a very large wingspan, which is larger than the 747-800, and its folding wing capabilities. And then the last step in the process, the FAA, my team will deliver those wake turbulence separation recommendations to the air traffic organization. From there, the air traffic organization updates its aircraft type designator documents and their automation systems to accommodate the new aircraft types. In order to provide wake separation recommendations, there are specifications and parameters that we need about each aircraft. This here is a non-exhaustive list of aircraft parameters we will generally request as a starting point. It includes the geometry of the aircraft, namely things like max certificated takeoff weight, max landing weight, max zero fuel weight, and various wingspans. For multi-rotor powered lift aircraft, like some of the proposed vehicles for advanced air mobility, this would be the aircraft geometry of rotor tip to rotor tip or rotor hub to rotor hub. We need a good understanding of the concept of operations, which is also an important factor in our assessment, especially where integration with crewed aircraft may be a factor. The vehicle speed for different phases of operation are especially important, and we will request different speed profiles for phases of flight like approach, departure, and any transition points, and any speeds associated with different configuration changes of those aircraft. We'd like to know how the aircraft will interface with other aircraft, whether the planned operation will occur on airport or outside the airport operations. We would definitely want to have more information on the aircraft's flight control performance, such as roll, pitch, and yaw rates, and any upset recovery information that we can obtain about the vehicle. In the cases of powered lift advanced air mobility aircraft, we are more concerned with this aircraft as a wake encountering aircraft rather than a wake generating aircraft. These parameters of roll, pitch, yaw rates, and upset recovery information will give us a better understanding of the aircraft's behavior when encountering the strong wake of another aircraft. Our research on wake turbulence is ongoing, and we will continue to monitor procedure development regarding the integration of advanced air mobility vehicles in the national airspace as regulations are codified. As more information on potential and planned operations of powered lift vehicles emerge, additional wake turbulence assessment could be required. For example, the design of route structures for the integration of AAM operations around current high-capacity airports. Our team stays connected to the different organizations within the FAA to make sure we are able to do those additional wake assessments when required. That can include the operational areas for vertiports, either on airport or near the airport, and the frequency of arrivals and departures. Our team is also anticipating the future transition of AAM operations to remotely piloted or autonomous IFR certified vehicles. For vehicles that are remotely piloted or autonomous, there may be changes in command and control functions or upset recovery characteristics. As the NAS is evolving to accommodate different aircraft types and operations, the FAA Wake Turbulence Research Program will continue to evolve and provide wake assessments with wake safety as our goal.
All right, Jillian, does that conclude your presentation?
It does.
All right, well, thank you, Jillian, first and foremost, for this informative presentation. It's really interesting to know that new aircraft like electric powered lift will still go through the same time-tested, science-based, and data-driven assessments that keep our skies safe. So as mentioned before, we now have some time to answer questions about today's topics. If you want to ask a question, please use the YouTube live chat function at the bottom of your screen. So we'll go ahead and get started. Let's see, our first question is, why are wake encounters a concern in the National Airspace System?
Sure. Wake encounters, they have a potential to create hazardous turbulence that could cause an aircraft to momentarily be uncontrollable. So we look at wakes in the terminal area. The main concern is a loss of control for the aircraft near the ground with insufficient altitude for upset recovery. Outside that terminal area, the unexpected loss of control due to a wake encounter is potentially hazardous with any unsecured flight crew, passengers, cargo. So you can understand where that loss of control would be a concern.
Understood. Yeah, makes complete sense. Our next question is, a lot of AAM vehicles are under 10,000 pounds. Why is wake a concern with those kind of operations?
Oh, sure. So for reference, the smallest category of aircraft is a small or light aircraft in the ICAO world. That refers to aircraft that are lighter than 15,400 pounds. It's a very exact number. The weight concern with these size aircraft is less about the wakes that they generate, but more about the wakes that they encounter. So they're lighter and more vulnerable in a wake encounter situation, especially in cases where they may be integrated with a larger commercial fixed wing aircraft like a Boeing 737 or an Airbus A320. So this can create a hazardous situation for all traffic. So we anticipate the potential of AAM vehicles to have flight control systems that are demonstrating more maneuverability than the traditional fixed wing aircraft. This can actually increase the amount of time that that vehicle may stay in a vortex during a wake encounter. And so that increases the hazard for that wake encounter as well. So understanding those types of parameters for that aircraft is really important for us, those command and control type of parameters for each of those individual AAM aircraft.
Yeah, that makes complete sense. I know I never really think about with air vehicles and things like that in terms of wake. I've always heard that with boats and maritime type things, but never using that same logic to and how it would affect, the airspace and things like that. So I appreciate your response to that question. And the last question that I have on my desk right now is, how are wake separations provided? If you could expand on that.
Sure. Wake separations, they're applicable when air traffic controllers are providing separation services. So air traffic controllers provide separation services during times such as when the traffic is operating under instrument flight rules. In visual conditions, typically separation is the responsibility of the pilot in command. So the separations that we are recommending to air traffic are the times when the air traffic controllers are providing those separation services.
Interesting. Yeah, makes sense. So we don't have any questions fielded from our audience just yet. So just please, friendly reminder, if you are in attendance for today's webinar and you would like to ask Jillian a question, this is the perfect time to do so. Please utilize the chat function at the bottom of your screen, and we can go ahead and get those over to ask Jillian. Looks like we have one from Houdini and a phone. Houdini says, when you discuss AAM, you keep using multi-rotor as the example. However, industry trends seem to indicate that the vectored thrust is becoming the dominant design. How is the FAA test transition?
Sure. So we are looking at all examples. We used multi-rotor just as one example of AAM vehicles. So vectored thrust is also one thing that we do consider. We are working with each aircraft individually. As they're coming in, we do assess aircraft on a airframe by airframe basis. And that's true whether that vehicle is an AAM vehicle, or if it's a fixed wing, something we traditionally see.
Sorry, I was on mute. Understood. Yeah, thanks so much, Jillian. Our next question comes from David Clooney, and David asked, Helicopters are known to generate problematic wakes when hovering and in forward flight, causing problems for other aircraft. Why is this not considered a problem for AAM aircraft?
So we are considering those the hover and forward flight pieces in our assessments for those wake separation recommendations. So those will be a factor as we consider them. Again, so since we look at these aircraft from an airframe by airframe basis, those are very individualized. The list of parameters that I gave that we typically look for is non-exhaustive. It's used to spark a conversation with either manufacturers or operators where we can get that data. And as that's a conversation that we continue. It's not a one and done type of we have the list and we get answers and we go ahead and do our assessment. The idea of that is that we have that back and forth conversation. So we really do our assessments on an airframe by airframe basis.
Gotcha. Well, thanks, David, for your question, and Jillian for your response. Our next comes from Brandon Smith, and Brandon asks, I know that atmospheric conditions were looked at already, but is there any effort to look at how forecast weather conditions can be used to predict the occurrence or dissipation of wake vortices?
So there's nothing specific to separation recommendations of advanced air mobility vehicles, but the use of weather conditions is something that we are doing kind of within that FAA wake turbulence, our research program. Our current program is to look at those dynamic wake separations for it's a later phase recat that we're looking at. And so we are looking to take advantage of, forecast weather conditions that would help dissipate that wake quicker, that wake decays. So the idea there is if there is a lot of wind at an airport, the wake dissipates faster, we may be able to reduce some separation between aircraft. So that is part of our research program.
That just sounds good. Thanks, Brandon. Hope you're doing well. Our next question comes from Joseph Stasiowski, and Joseph asks, AAMs utilize vertiports. There wouldn't be much wake turbulence. However, are other turbulence factors being studied for the AAM airspace, for example, wind tunnel effect in cities between buildings? So
I believe there may be some research being done on that. It's not being done by my group. So my group is specific on wake turbulence. There could be wake turbulence as a factor between AAM vehicles. So I did kind of dismiss a little bit on the idea that we don't look at the AAM vehicles as a wake generator, but in these AAM vehicle to AAM vehicle operations to vertiports, that could be a factor. So we do still consider the generation idea and the vertiport operations. There will be, I'm sure, future research coming up, more wake assessments that need to be done as vertiport operations are kind of being defined as AAM vehicles our operations are being nailed down and defined.
Gotcha, makes sense. Well, thank you, Joseph, for your questions. We don't have any more questions in the queue right now, so please, audience members, if you'd like to ask Jillian any questions live in today's event, please feel free to take advantage of this opportunity. While we wait for some more questions to come in, Jillian, if you don't mind kind of just expanding on your background, how did you become interested in wake turbulence research and how you got into this position you are today, if you don't mind expanding on that?
Yeah, sure. So as Jessica mentioned, I actually started as an intern at the Volpe Center in wake turbulence back when I was an undergrad at Boston University. I was studying aerospace engineering. And so the current wake program at the FAA, that's the program that I started with. That was over 20 years ago. And I did mention part of the late 90s, early 2000s, some of the data collection efforts that were going on then included a wind line. And I was part of a team along with my Volpe Center colleagues who are still part of the team to this day, building the wind lines out in St. Louis. So we built like a line of propeller anemometers, with our blood, sweat, and tears, kind of gluing PVC pipes and, calibrating these anemometers to collect that wake data. And so that's where I got my beginnings as a college intern, actually from Boston University. I transitioned through various employers, but always working wake. So I went from the Volpe Center to the MITRE Corporation for several years doing concept development and safety work. And then I worked as a contractor for the Agility Corporation, continuing that safety work within the wake turbulence arena and doing, the safety work for wake recat, for that matter, until I came and joined the FAA in 2016.
Well, that's awesome. Sounds like you've had a lot of experience in the industry and it's taken you to a lot of great places. I was interested too, in your presentation, you mentioned, I believe it was JFK and SFO Airport.
Yes.
All my family's in the Bay Area. So did you ever get to go out to SFO's airport and do any hands-on testing there, or was it mostly from
when the SFO site was being put up, I was no longer doing that type of field work, but we've seen where our sensors go. We've got quite a few LiDARs out at San Francisco. It measures both wakes that are further up the glide slope in that out of ground effect region. And we have a few sensors measuring that in ground effect, near ground effect region at San Francisco. We chose San Francisco and JFK because they have a good fleet mix of wake generating aircraft. So they have a lot of heavy, a lot of large traffic. Heavy aircraft would be like the 747s and the 787s, the 777s. The large aircraft go from, the 737s, the A320s, 319s, and such like that. So both San Francisco and JFK have a good fleet mix for looking at those larger aircraft that have the stronger wakes.
Yeah, it makes complete sense. Like you said, a wide variety of aircraft, all different shapes and sizes. And you might have mentioned it already too. I think you mentioned ICAO. Are there any airports, let's say some of the busier airports, obviously SFO and JFK are some of the busiest ones stateside. Are you guys teaming with anything over in Europe in terms of their larger airports to see if there's any, ways we can strategize together on these kind of things?
We haven't put any sensors out in Europe, but we have partnered in the past with Eurocontrol and some of the, the Dutch and the German aviation research centers. And so we've been, we've got, colleagues that have worked kind of across the pond, I would say, with Europe. We did harmonize. We were working together for the RECAT effort. They do have a RECAT EU version that gets brought to ICAO, and then we meet up at the ICAO. There is a wake turbulence specific working group that we work together on.
Oh, that's awesome. It's really
That's
cool.
international work, yeah.
Yeah, how it's all intertwined together across the globe. Looks like we have another question in the chat from Johnny, and Johnny asks, in built-up areas, how are you going to measure mechanical turbulence? Wake turbulence can be significant on one approach to a building rooftop, but on the other side of the building, there is none.
So, so the wake turbulence refers specifically to the vortices coming off of the aircraft wing rather than the buildings. So we do kind of look at our data built into models. When we collect our data at the places like San Francisco and JFK, these are, real aircraft in real wind conditions. And so in our database, we have, the depiction of wake behavior in our database associated with the ambient environmental conditions. And then we were able to kind of pull out the relevant data for certain situations based on what we're assessing and apply it that way.
Thanks, Johnny, for your question. Another question that comes to mind is, what considerations will need to be made when AAM are no longer crewed?
So again, command and control is a big factor for us. So crewed could mean air pilot in the cockpit, or it could be remote pilot. And so there are differences in there as well. Your reaction time for encountering a wake could be different if it's automated, if it's if it's a pilot feeling that wake turbulence encounter in the cockpit, like on their body, or if it's a remote pilot kind of relying on sensors if they've hit a wake. So the reaction time plays a factor, and what type of response the aircraft has, either automated or piloted, would make a really big difference in terms of what's what the separation could be.
Yeah, no, it makes complete sense. I appreciate you spelling that out for me. And I know in your presentation too, you mentioned data collection over the past 20 years. I mean, that's a pretty long time. How much data do you actually have, and what do you use it for?
So we use it to drive any safety assessments that need to be done, new procedures that are coming on board, you know, not necessarily AAM related, but you know, if you know an airport wants to better utilize things like closely spaced parallel runways, they might design a new procedure, and our wake data will help inform the safety of that new procedure. In terms of the amount of data, we've got a lot. We're talking, you know, lots of terabytes. All of that data is stored and run from my colleagues up at the Volpe Center, which is, you know, when I refer to my team, we've got a team from the Volpe Center. We work with, you know, folks from MIT Lincoln Lab and various SMEs that we've had.
Gotcha. That makes sense. Let's see. I'm wondering if we have any more questions in the queue. Let's see. Looks like we have one last question. It says, how will FAA Office of Next Gen incorporate the findings from the 2023 Noise Policy Review and 2021 Neighborhood Environmental Study into AAA operations planning relative to wake turbulence research?
So I think noise and the wake turbulence research are a little bit decoupled. So I'm not sure if we have specific plans for that, but you know, we continue to work closely with other lines of business in the FAA, and when there is a wake issue, we're ready to respond for any type of concerns.
Makes sense. Yeah, it's an ever-changing product and process. So thank you, yeah, Jillian, for all your responses to today's submitted questions. Seems like that's going to wrap up today's Q&A portion for today's AAM webinar. But thank you again to Jessica for the introduction, but also Jillian for your presentation and webinar. And thank you to everyone in the audience who joined us for today's update. Next month, we partner with the Association for Uncrewed Vehicle Systems International for a webinar panel discussion on airspace integration impact assessments on March 13th at 3 p.m. Eastern Time. Meanwhile, please visit our webpage at faa.gov/air-taxis for the latest updates, including information about future webinars. Thank you, and I hope you all have a great day. Take care.